Hello, this is Mr. Stansbury. I'm going to take you through the 1B notes on number sets. At the end of this, you should be able to say, I can recognize and classify any number into the correct number sets. Okay? So, first thing, let's talk about all the different types of numbers that we've got going on here. Okay? So, N with the star are the numbers 1, 2, 3, and 4. That is considered to be the set of all the counting numbers, because we usually start with 1, and so forth and so on. Okay, and without the star is 0, 1, 2, 3, 4. So it's the same here, except for just added in 0, and that's the set of all natural numbers. The Z is 0, and then plus or minus 1, plus or minus 2, plus or minus 3. This is the set of all the integers. Okay, and I often remember that that's integers because I think of that as integers, like with a Z on the end, but I don't know. Whatever floats your boat, whatever works for you. Z with the plus is 1, 2, 3, 4. It's just the set of all the positive integers. Okay, and then Z with the minus is -1, -2, -3, -4, which is just the set of all the negative integers. Okay? Q is you have P over Q, where P and Q are both integers, and then Q cannot equal 0. Okay, so you've got some number over another number. If you can represent a number as some kind of fraction, then you consider it to be a rational number, which is Q. Okay, and over here you might ask, like, what's this whole Q can't equal 0 business? If you think about it, if you put 0 down here in the denominator, then that is bad news, because we know we can't divide by 0, right? And that makes the math gods angry. So don't do that. So make sure you just can't put 0 in the denominator. Okay, and then the last one is R, and sometimes you see that R is the R with the second line through it, kind of like the little paragraph symbol. And those are real numbers, and that's basically all the numbers that you can place on some kind of number line. Okay, and you might have noticed that, look here, if you notice that our Z plus and our N, these two things here are the exact same set of numbers, 1, 2, 3, 4, 1, 2, 3, 4. So the positive integers are the same thing as the counting numbers. Okay? Okay. Now that we have that, we are going to show that some numbers here are rational numbers. Okay, so again, if you'll remember back to what we had before here, rational numbers is just any number that you can represent as a fraction. Okay, so let's do that. So if you look at this here, you got 0.45. One way that you can read that is 45 hundredths, right? So right there we have expressed this as a fraction, so then therefore we've shown that it has to be a rational number. What you also want to do with this here is you want to simplify this as much as you can. Both of those are divisible by 5, right? So that's 9 over 20. Okay, so that's even better. So we've shown that this one here is rational. And then 0.135, you can read that as 135 thousandths, right? And we can simplify this one as well. And let's see, let's divide both of those by, let's see what's going to work. So yeah, we can divide both of those by 5 also, and that's going to end up simplifying down to 27 over 200. Okay, so we have now shown that those are rational just because we expressed them as a fraction. All right. Okay, next one, example 4 from page 21. Show that 0.777 repeating and 0.3636 repeating are rational numbers. Okay, now this is a little trickier. What we got to do here, we want to show that these things truly are rational numbers. So I'm going to show you how to do that, and then I'm going to show you like a much simpler, shorter way to show that these things are rational numbers. Okay, so now work with me here. Just try to understand what the heck's going on here, and we'll be just fine. So we're going to do this for starters. So let's say let x equal 0.777, repeating. Okay. And then what we're going to do is we're going to multiply both sides by 10. So then we're going to say, okay, if we multiply both sides by 10, we've got 10x equals 7.777, repeating. Okay. And then all we're going to do is split this up over here. So we're going to say 10x is equal to 7 plus 0.777, repeating. Right? And we now know, we know from originally this x equals 0.777, so I'm going to replace this 0.777 with an x here. So now we have 10x equals 7 plus x, because again here x equals 0.77, so I'm just going to replace that with x. Okay, and now we can subtract x from both sides here. So we get, let's do that, subtract x from both sides. That was not a pretty line. That's a little better. 9x equals 7, and then we divide both sides by 9. So this x here has to be 7/9. So now we have shown that this here, 0.777 repeating, is 7/9. Okay, so we've now shown that it's rational because we expressed it as a fraction. Okay, same idea here, and we're going to do that. It's just now it has two different repeating numbers, so we'll do this. Let x equals 0.3636, repeating. Okay, and we're going to multiply both sides by 10, so now we have 10x equals, actually, we're not going to multiply by 10. Since there's two repeating decimals, we want to multiply by 100, so now we have 100x equals 36.3636, repeating. Okay, and then we're going to break this up into, we've got 100x over here, and we're going to do 36 plus 0.3636, repeating. And again, remember, this 0.3636 is the same thing as x. So now we do 100x equals 36 plus x. So we subtract x from both sides, and we get 99x equals 36. So we divide both sides by 99, and we get x equals 36 over 99, and we've now shown that this is also a rational number. Okay, now hopefully you can kind of look at this and figure out the pattern. It's like, there's one repeating number, and it ended up being that repeating number over 9. There's two repeating numbers, and it ended up being those two repeating numbers over 99. So hopefully you can make the jump if they gave us an example of, say, 0.412412 repeating. There's three repeating decimals, so it's going to be 412 over that many 9s. Okay? All right, I know that was kind of a weird one. This is how you show it, and this is our nice little shortcut. Okay? Okay. Last thing here, we've got irrational numbers. Okay, irrational numbers cannot be written as a fraction. They can't be written as p over q. Examples of irrational numbers are root 2, pi, and the square root of 29. Okay, so none of those things there are rational, so they're all called irrational. Okay, now here's the big key here. This is how you can tell if something's irrational. Irrational numbers never end, and they never repeat. It has to be both. They have to both. Has to be both never ending and never repeating. Okay, so for example here, rational or irrational, 0.712. This one ends. This one terminates, we call it, and we can write that as a fraction, 712 over 1,000, right? And then we could simplify that. But either way, we know that that is rational. Okay, square root of 71. If you bring up square root 71 on your calculator, you get 8.426197773 da 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 da. It's a decimal that goes on forever and ever, and it never repeats. So it fits this irrational number definition here. It never ends and it never repeats. So this here would be irrational. Okay, and this here, the 0.4949, this is the one we were just doing before. We know that we can represent this as 49 over 99. So this one here has to be rational. All right? Okay, you should now be able to say I can recognize and classify any number into the correct number sets. If you have any questions, please ask. Thanks.